Welcome back. We've seen the complicated math behind how neural networks learn, but how do we actually take that math, the algorithm of backpropagation, and adapt it to solve totally different types of real-world problems? It all depends on the task. Let's start with what we call a feed-forward network. The rule here is simple. Information travels strictly on a one-way street. Data enters on the left, moves through the hidden layers in the middle, and exits on the right, without ever reversing. This one-way structure works well for static, unchanging problems. Imagine a scanner reading a piece of paper to identify the letters printed on it. The text isn't moving or evolving. The network looks at the image once and makes its best guess. You interact with another static network every time you check your email. A spam filter reads the sender's address and the content of the message in a single pass, then outputs a simple decision: spam or not spam. If that filter makes a mistake, backpropagation kicks in. It calculates the error and walks backward along that one-way street, adjusting the connection weights from right to left so it can do better next time. Think of these networks like a straightforward assembly line. They excel at tasks where the entire problem can be evaluated in a single, frozen moment in time. But what happens when the problem isn't frozen? If you are dealing with information that unfolds over time, a static network struggles. Understanding what is happening right now often requires remembering what happened 5 seconds ago. To handle a steady stream of time-sensitive data, we use recurrent neural networks. Instead of a strict one-way street, these networks feature internal loops. They take the output from a middle layer and feed it right back into themselves alongside the new incoming data. That looping structure creates a form of short-term memory, which is crucial for unpredictable, continuous information. Take stock market prices, for instance. You can't predict a stock's next move just by looking at a single price tag. You have to understand the context of its ups and downs throughout the day. The same logic applies to forecasting the weather. Tracking a hurricane requires a network that remembers yesterday's pressure drops and wind speeds, combining them with today's readings to figure out where the storm is heading tomorrow. Backpropagation still works here, but it has to adapt. The math has to repeat itself in loops, tracing the error backward through the layers and even back through the history of the data itself. By adding these loops, we move past simple pattern recognition. The network becomes a dynamic system capable of grasping context, history, and evolving trends. So we have different network structures for different problems, but actually getting these networks to learn presents a massive physical hurdle: computation time. To take a single, perfectly accurate step in the right direction, the backpropagation algorithm technically needs to look at every single example in your training data, figure out how each one wants to adjust the network, and average them all together. If your dataset has tens of thousands of images, doing that math for one single adjustment takes an incredibly long time. Your computer would be stuck staring at a mountain of data, calculating for hours just to take one tiny step downward toward a lower error rate. If we relied entirely on that perfect, comprehensive calculation for every step, practical machine learning would grind to a complete halt. It is simply too slow. To bypass this, computer scientists use a randomized downhill crawl, an approach technically called stochastic gradient descent. Look at this graph representing an ocean of training data. Instead of evaluating all of these data points at once, the algorithm randomly shuffles them and chops them up into bite-sized mini batches. The network then calculates its next adjustment using only the data inside one single mini batch. It ignores the rest of the dataset for that specific moment, figures out a rough downward direction, and takes a step. Think of the traditional perfect method like a hiker trying to get down a mountain by pulling out a compass and a map, spending hours measuring the exact mathematical angle of the slope just to guarantee their next footstep is placed flawlessly. The mini-batch approach is more like a hiker who stumbles aimlessly downward. The individual steps might be slightly off target or zigzag a bit, but because the hiker doesn't stop to overthink, they move incredibly fast. The stumbling path is definitely messier. But taking hundreds of rapid, good enough steps gets the network to the bottom of the hill vastly quicker than slow, perfect deliberation. All of these architectural designs and clever mathematical shortcuts rely on one final, indispensable ingredient. You need a massive amount of training data. A neural network only knows it made an error if it has an answer key. Without tens of thousands of explicitly labeled examples, like human-curated databases of handwritten numbers, the network has no baseline to measure its own mistakes against. This is true across the board. Whether you are training a static network to filter spam emails or teaching a recurrent network how to pronounce a human name correctly, it needs a massive backlog of correct examples to learn from. Because of this, gathering, organizing, and physically storing huge quantities of accurately labeled data is often the most resource-intensive phase of any machine learning project. The algorithm is useless without the raw fuel to power it. Backpropagation works as a repeating cycle of trial and error, adjusting connections one quick, stumbling step at a time. Ultimately, if we have enough past mistakes to learn from and a fast enough way to process them, a simple cycle of trial and error can solve some of our most difficult real-world challenges.